Let's wait for some time. Let's see how many joins. We will start at 6 to 6:30. So okay, let's start. Hello everyone, my name is Rijoy Mukherjee and I am a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. I will be taking this live session for NPTEL course on operating system fundamentals. We will be solving some problems of this week course. Hi, am I audible? Am I audible? Can you hear me? You can type also if you can hear me or not. Yeah, okay, so let's begin this week's doubt clearing session. So, if you have attended previous classes, or you will know that we will be discussing this week's course, that is course 11, in a little depth. Then we will be solving some problems related to week 11. So, if you have any doubts or anything, feel free to ask anytime in the chat box or directly ask the questions. So, let's begin. So this week, let's discuss what we have done previously. So previous week we came across the concept of pages, that is basically a subpart, division of process into smaller parts, into equal smaller parts, right? And we also came across various uh, TLB for faster access of pages. We also came across virtual memory and the reason we use virtual memory, right? So virtual memory, we showed that if we are if we are, so at a time the CPU doesn't need to run a process, you don't need all the pages of the process, so you can keep few pages of the process in your main memory and execute it, and the rest of the pages of the process can be stored in the virtual memory, or let's say the secondary memory, and from there when and you as required you can access it. We also came across the term called demand paging, which means a page is brought in the main memory only when the CPU needs it. So we also came across this concept of demand paging and everything, which is basically that whenever you need a page, only then when you bring the page into the main memory, else don't bring it. So these are the various concepts which have already been covered. So let's dive into this week's ones. So first we will discuss the performance of demand paging. So in demand paging, 3 steps occurs. So first is you service the interrupt, read the page, restart the process again, just a small amount of time. So these are the 3 major activities that takes place in case of a demand paging. Service the interrupt. What is the interrupt? Interrupt is basically your request to bring the page. Then you read in your page, and then you restart the process again, just a small amount of time. So page fault rate. So page fault rate is basically a fraction. This is the range of value between which your page fault rate occurs. So if P is 0, then there is no page fault. If P is 1, that means every reference in a page fault. So P is 0, no page fault. This can only occur if there are huge number of frames in your main memory, and the program is sufficiently small enough so that it can remain in any of the frame. Like our frame is always empty for any page. So that's why no page fault occurs in that case. P is equals to 1 means every reference in a page fault. So it may be the case only that only this box is free. Only this box is free. So at a time, all the time you bring in a page, all the time you bring in a page, all the time you bring in a page, whenever you require it. So that is your demand paging. Page fault rate, when page fault rate is 1. So effective access time, EAT in each case is basically your what is this? This is your non-page fault, number of times so suppose if it is p times there is a page fault, so that is this p times, and what is the overhead in case of a page fault. So one is page fault overhead, and then is swapping a page out and swap a page in. So basically you have, so when there is a page fault, so these are your frames, right? So a page fault occurs means you don't have the page in your main memory, you need to bring it to the main memory. So that process of bringing the a page in is basically your swap the page in. Now a case may be there is no free page here, free frame remaining here. So in that case you have to page out one of the swap one page out, right? So that is your overhead for swap one page out. And then there is a page fault overhead. What is a page fault? Page fault is basically simply your whenever you are requested a page, and page not present in main memory. That is basically your page fault. So that overhead, then the swapping a page out and swapping a page in, that is your overhead when there is a page fault. And when there is a no page fault, that means the only overhead is your memory access overhead, right? So that is your effective access time for any programs, any processes frames. So any doubt regarding this paging, this question? Okay, so let's go to the next one. So this is your this EAT example. So you have a memory access time of 200 ns. You have an average page fault service time is 8 milliseconds. So your average EAT is 1 minus 8 into 200, and when there is a page fault, that is this. So ultimately the equation comes down to this. If one access out of 1000 causes the page fault, then EAT is 0.8.2 microseconds, right? So a slowdown is by a factor of 40. So this is a typical example with numerical values. You can expect some questions regarding this in any exam you sit for, any competitive exams, or in your college, or even in the NPTEL exam, you can expect some questions like this, or access time and all. Let's now come to this topic of how can you optimize the demand paging optimization. So what you can do is swap the IO faster than the file system IO, swap space IO faster than the file system IO, even if it is on the same device. Swap allocated in larger chunks, less management needed than the file system. So what they are saying is, when you are swapping in and out, you swap in a large portion into the memory. So this comes from your locality concepts, like what you have seen in your TLB. So what you used to do in TLB, you used to bring a chunk of pages from your main memory directly into the mainframe, because you predict that further reference will come from that next reference of the frame of the page may come from the lot you have selected. Yeah, like you can think about of this like a C code which you have written. Let's say like adding of 10 numbers, 100 numbers. So you've written a loop and it is adding 100 numbers. So what you can do is, so the loop is, let's say, your for loop. So in a for loop, what you have, you will have uh, assignment operator, you will have a assignment statement, you will have a logic check statement, and the third part is your incrementing the I. So if it is a logic check statement, after that it will also already always increment the counter, right? So next fetch will always be that. So in that way, that is the reason that will be the next page always formed. So it is better to keep it in the TLB. So a similar concept is here. So swap allocated in large chunks, less management than file system. So the second is copy the entire process image to swap space at the process load time. Then the page in, then page in and out of the swap space. This was basically used in older BSD Unix files. So there is this thing called swap space, and there you can keep your entire process image. Demand paging is in from program binary on the disk, but discard rather than paging off when the freeing frame. So this concept is basically used in Solaris BSD. Still need to write to the swap space. So again, still you need to write it to the store space. Pages are not associated with a file like a stack or a heap. Pages modified in memory but not written back to the file system. So these are the things that still problem. So in mobile systems that you currently have, they typically do not support swapping. Instant demand paging from the file system and reclaim read-only memory such as code. These are just some optimization techniques and nothing more. Now this is an important concept, copy on write. So the concept comes like this. So this is your CPU, this is your main memory, so this is your CPU, this is your main memory, and this is your secondary memory. So you know that virtual memory is basically your main memory along with your secondary memory. So CPU knows what? Logical address, right? Not the physical address, because the physical address is basically you don't know, because physical address here refer to your main memory address, but your some part of the process of the pages can be stored in your secondary memory also. So now you also have this problem that more than one process can share a page, right? So let's say you have this process. So let's say this is a page which is shared by more than two processes. Let's say P1 and P2 both share this same page, right? Now let's say P1 has modified this. Let's say P1 has modified this this one, this process only, this page only. Let's say it has modified something here. Now since it has been modified, obviously P2 will be also using the modified version, right? P2 will also be using the modified version, right? So, but at some point you need to swap this one out here, right? Then what happens? So P2 doesn't P2 doesn't want the updated copy. I know it is sharing it, but it wants the previous one. So what happens in that case? In that case, only the copy happens. So what I mean to say is this. So you have your main memory. And let's say this is the process that is shared by both P1 and P2. And now let's suppose P1 modifies it. So in that case, whenever it writes on this page, a copy of it is created, such that P1 refers to the modified copy, whereas P2 refers to the non-modified copy. Whereas P2 refers to the non-modified copy. That is what you define by the concept of copy on write. So the copy happens of the data only when you are writing something onto the page. Okay. So let's go through this once. Copy on write allows both parent and child process to initially share the same pages in the memory. If either process modifies the shared page, only then is the page copied. COW allows more efficient process creation, only modified pages are copied, right? The same thing. Free pages are allocated from a pool of non-zero pages. Pool doesn't always have free frame as fast depend. Do not want to have a free frame as well. Those kind of things occurs. So vfork is a version of fork system call that call has parent, suspend, and child using a copy on write address space vacant area. So designed to have child call exe, this kind of thing. So this basically is the concept of your copy on write. If you have studied the subject of computer architecture, there also you will find this copy on write concept for cache. So what happens there is that multiple cores are sharing are using the cache at the same time. So if somebody modifies the cache memory, when do you write back the cache? So there also this copy on write concept is used, and it is quite similar to that. Okay, so let's go to the next one. So this is the concept which we are doing that. So here process P1 and P2 shared 3 pages, page A, page B, and page C. Now process P1 modifies page C. So what happens? Process P1 now has its own copy of page C, and process P2 is holding the old one. That is what I tried to explain in the previous slide. Now we come to a very important topic of page replacement. So what do you mean by page replacement? So let's quickly come to this. So what is limited? Is VM limited? Virtual memory limited? Is virtual memory limited, or is main memory limited? Yeah, so your so VM can be considered as unlimited. Like, let's be honest, VM is unlimited, right? Your laptops have 1 TB, 2 TB of your memory, whereas ROM, but your main memory have been just stuck at 8 GB, 16 GB. So yeah, you can consider it as a very high limitation, not infinite limited, but high limitation. Yeah. So so as a result, so your main memory is limited, right? So what are the frames? Frames are typically what we have in your main memory, right? So this is your frames in main memory. Right. Now we need to allocate pages into the frame. Right. Now where are the pages stored? Pages are in your virtual memory, and you need to bring them to your main memory, right? So whereas your pages are large in number, frames are small. Let's say limited. Okay, so at a time that means all the pages cannot be present in your main memory, because all the frames will not be empty, right? So as a result, you need to bring in you need to that concept of swap out a page. So let's say currently all of the pages, all of the frames are full here. So these all are full, they are not empty, they are occupied by some page. So what we need to do is we need to swap out, let's say this is your VM. So we need to swap out a page from here to there, and we need to swap in a page from here to here, right? Whenever a page fault occurs, in case of a page fault. Right. So this process is one of this swapping in and swapping on, right? So this process is basically your page replacement. Your page replacement. And as you will further go in this today's session, we will see that we will discuss much different kind of page replacement algorithms, because this has to be a little bit prioritized, like which one we need to swap in and swap out, which memory should we swap out. That has to be a logic behind it. It is not that, oh, this one has been used now, has not been used for a long time, so let me swap it out, or this one came first, so let me swap this out first. It is not a stack or a queue kind of setup. These are in in your Unix machines and all, there are particularly very not a primitive algorithm, quite complicated algorithms to do this kind of replacements, and we will look into it one by one. So any doubt regarding page replacement? Okay, so let's go. This is another topic, like I can assure you, like if you are sitting for GATE exams and all, this one question will come. So this page replacement, and like previous week we did that, what we did, that that access time questions, those questions regularly arrive in one. So again, there was that best fit, worst fit one. Those questions quite, like every year they give one question on that. Okay, so a page replacement occurs when a page fault occurs and we need to bring the desired page into the memory, and there are no free frames. Page replacement finds some page in the memory, but not really in use, that it pages it out. So there has to be an algorithm which decides which frame to free. Performance want an algorithm which result in minimum number of page faults. So why? So it cannot be like this, that suppose let's say these are your frames available, and you have designed an algorithm where after, let's say these are all full, let's say they are all filled up. So when a new request comes, then there will be a page fault, right? When a new request comes, there will be a page fault. Now you need to design algorithm such that after like after every page fault, like it is not that for every page fault you need to what I mean to say is, it is not that every time there is a page fault and why that it would be. So suppose let's number this like this. Let's number these frames like pages like this. This is page 1, page 2, page 3, page 4 and page 5. Let's say now a request comes from page 6. So a solution can be, you replace 1, you swap out 1 to your VM, and then they bring you 6. Now let's say the next page which CPU wants is page 1. Now page 1 you have recently swapped out, but the CPU is now requesting page 1. That means again there will be a fault, right? Then there will be a fault because you have just removed that from the main memory and you now have to again bring that from the virtual memory. So this will be a fault. Suppose the next time you swap out page 2, fine. But again the next request comes only page 2, then it will be again a fault. So we want an algorithm which results in minimum of this number of page faults. You need an algorithm which requires a less number of sweep fault. It's quite simple to say, but there are not many algorithms which does that. So we will look into this. Let's look into some of the algorithms one by one. Yeah, so this is an example of a need for a page replacement. So this is your physical memory. This is logical memory for user 1, and this is a page table. So, so and this is all the frames have been used. This is page table for user 2. This is page table for logical user 1. So user 2 needs B. So you see all of them are currently full. So you need a page replacement in that case. So that is what it is meant. Okay, let's go to the next one. So use the modify dirty bit to reduce the overhead of page transfers. Only modified pages are written back to the disk. So if you look at here, these are your valid invalid bits or those things. So only the modified ones will be pushed back. Page replacement completes separation between logical memory and physical memory. Large virtual memory can be provided on a smaller physical memory, like that what I meant. If you if you have noticed here, we meant that only, that large physical memory and small physical memory and large virtual memory we have, and that is what page replacement algorithms are trying to do. Now we'll have a go through at this basic page displacement algorithm. So first we find the location of a desired page on the disk. So the page we want, we find that on the disk. If a frame, free frame, if there is a free, then we search for a free frame. If a free frame is present, then we use it. If no free frame is present, then use a page replacement algorithm. Find a victim frame, write the victim frame to the disk if it is dirty. Bring the desired page into the new frame and update the page and the frame tables. Continue the process by restarting the instruction that caused the trap. Quite plain and simple, what we discussed previously. So you have your frames, and here you have your main memory. So you swap out you swap out this from here, and you only write it back. So you only write it back if it has been modified, else you can just drop it, right? You have to write it back to the physical memory only if it has been modified. So copy on write, remember that one only. And you swap in, and you may swap in this. Yeah, so you swap in back this only when it is required. So you swap it here after replacing it, right? So that is your basic page replacement algorithm. So you just find a page free. If there is no page free, then only then you swap one out and swap in the desired page from your main memory. So this is your algorithm that I was discussing. So you will have your valid invalid bit. So and so the valid invalid bit uh, gives the indication that whether it has been modified or not. If modified, then write back to physical memory, right? So that is your one basic page replacement algorithm. So your frame allocation algorithm determines how many frames to give to each process and which frames to replace. So your so you have a large chunk of frames, right? But you want to like you want your CPU to access multiple processes at the same time. So what you do, you obviously that's the reason we have your virtual memory, and only a part of the process, some of the pages are present in the main memory. So your frame allocation algorithm can do something like this. It can say that only this set of frames can be used by process 1. So that they can uh, determine. They can say that, okay, only this set of processes you can use. Only this set of frames you can use. So that is determined by your frame allocation algorithm. Then your page replacement algorithm, the desire is we want the lowest page fault. So our main objective or the optimization part of our what this page replacement algorithm wants to achieve is lowest page fault rate objective of PR algo. So there are many evaluation algorithm on a particular string of memory references and all. So so here is an example of a reference page number. So first is request page number 7, then 0, then 1, then 2, dot dot dot. This is a reference line of, let's say, a page has been requested like this. So here is an important graph. So graph of page fault versus number of frames. So you see number of frames increases here, and number of page, these are the number of page faults. So as you can see, at a certain point you get that perfect balance where number of page faults let me just elaborate it a little bit. So if you look at the graph, what does this indicate? That for 1 to 3 number of frames, less number of frames means more page fault, right? So if you are given a graph like this, what you will think is that for 1 to 3, the number of less number of frames is correlated with the more page fault. But as you notice here, beyond a certain point, number of page fault is not dependent on page size. Number of page fault is not dependent on number of frames. So beyond a particular point, it averages. So after this point, it doesn't matter how many page frames you have, 5, 6, 7, 8, the faults will be minimum, right? So after a certain point, the number of frames is no more in the equation. It will be same, the page faults. Not inversely proportional. Inversely proportional is only for, let's say, page 1, 2 and 3. See, after that it has no relation. For 4, 5, 6, the curve completely goes out flat. That means it is no more a factor in that. The number of frames is no more a factor in your page faults. Initially it was inversely proportional for 1, 2 and 3. This is probably your exponential graph, like inverse exponential graph. So let's try out this algorithm. First in, first out algorithm. So you have this reference number of page requests, and you have 3 frames. So we will calculate how many page faults are there. So initially it is all empty, right? So when 7 is requested, that means it is 1 page fault. So this is 1 page fault. Now 0 is requested, another page fault. Now 1 is requested, sorry. This is a page fault, this is a page fault. Now 1 is requested, another page fault. Now 2 is requested, first in, first out. That means the frame that has been inserted first will be the one to get out first. So 7 will be evicted. So this is also a page fault because 2 is not present. So this is also a page fault. Now 0 is requested. Now 0 is already present here, so that is not a problem. Now 3 is requested. Now the last one to which is the first one here at this case, 0. So that is a page fault when 3 is requested. Now 0 is requested. See, this is a problem which I said. So we will define this problem that after this sometime. So you have affected 0, but now you require 0 again. So this is again a page fault. Now 4 is requested. 4 is not present here, so that is also a page fault. Now 2 is requested. 2 is not present because you have just affected 2, so 2 is also a page fault. Now again 3 is requested. Again a page fault. 0 is requested, another page fault. Now 3 is requested, 3 is already present, no more a page fault. 2 is not already present, not a page fault. 1 is requested, page fault. 2 is requested, page fault. 0 is requested, it is already present, not a page fault. 1 is requested, already present, not a page fault. 7 is requested, not present, that's why a page fault. 0 is requested, not present, page fault. 1 is requested, not present, a page fault. So in total, if you count this 4 plus 6, 14, 14, 10, 12, 15. So there are total of 15 page faults. Okay, so have you understood like wow, what is a page fault happening here and all? Okay. Okay, so let's go to the next one. So next is number of frames versus page fault. So so now we will again come back to that number of frames versus page fault. So consider this is your page request. So how many page fault will be there? You have 3 frames, and how many page fault will be there if you have 4 frames? So let's do it. Okay, let's do it. So you have 1, 2, 3, 4, 1, 2, 5. Let me write it down. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 5. 1, 2, 3, 4, 5. So let's consider the 3 frame case. Okay, so you have 3 frames. So let's first consider this one 1. So yeah, it is a page fault. Then 2, page fault. Then 3, 1, 2, 3, page fault. Then 4. So this is a FIFO. So the first in first out. So this will be overcome. 4, 2, 3. Then you request 1. Very good. Again 1 evicted. 2 will be evicted. 4, 1, 3. Then you request 1, 2, 3, 4, 1. done. So now you request again 2. Okay, fine. So you got out 412, another page fault was there. Now you request 5. So 5 will be swapped out. 4 will be swapped off. 5, 1, 2. Now 1 and 2, there is no issue, no page fault. Now 3 is requested. So this will be swapped out. 5, 1 will be swapped out. 3, 2. Then 4 is requested. 5, 3, 4. And then 5 is requested, which is already present. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 page faults. Right. Now look at the 4 frames. So 1, 2, 3. Okay. So there will be typically 4 page faults. 1, 2, 3, 4. 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Right, there are 4 page faults already. Next, 1 is requested, 1 is already present, 2 is requested, already present. Now 5 is requested. So 5, 2, 3, 4, 1 page fault. Then 1 is requested. Then that means 2 will be evicted. 5, 1, 3, 4. Then 2 is requested. Another page fault. 5, 1, 2, 4. Then 3 is requested. 5, 1, 2, 3. Then 4 is requested. 4, 1, 2, 3. Then 5 is requested. 4, 5, 2, 3. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 page faults. So that means by increasing the number of pages, we are getting more page faults, right? So that is a problem of this FIFO allocation. This is called basically your Beladis anomaly. So if we use FIFO for page replacement, we can encounter the anomaly that more frames may lead to more page faults. So 9 for your 3 pages and 4 for your for 4 you need 10 page faults. This is your Beladis anomaly. So if you use FIFO for page replacement, we encounter this anomaly that more frames may lead to more page faults. Whereas our graph was something like this, right? So this is a problem with FIFO. So any doubt regarding this so far? Fine. Okay, so let's go to the next one. So let us look at an optimal algorithm. So in this algorithm, what we do is we replace the page that will not be used for the longest period of time. Okay, so what does this mean is we will predict the future. So we will say that this frame will not be used again for a long time. But we are not God, we are not an oracle that that we will come to know, our system will come to know that which one will not be used for the long time while eviction, right? So this is your optimal algorithm, but this is not possible, right? So so if you these are basically improbable, but still they have shown it. Like, so here you have the string. So at this point, when you have to replace a, so here when you are requesting 2, you need to replace one frame. So which one will you replace? We will replace the 7, because we see that 7 is not requested in a long time. So 7 will be evacuated from its frame. But that is not a normal system behaves. In ideal case, if somebody knows the future, then for him or her, this is a best case scenario. But we don't know the future. So this is very this algorithm is not much useful in our case then. So we will use something different. We'll use the past knowledge rather than the future. So this is called your least recently used algorithm. So we'll replace one which has not been used for a long time. So let's look into it. So in the optimal, how many page faults were there? So in the optimal, there are 9 page faults. So this is the optimal where you know the future. So in FIFO it was 15. FIFO 15 and optimal is 9. So in least recently used, we will do this again. So for 7 is requested, a page fault, correct. Seven is requested, it is a page fault, correct. Then 0 is requested, a page fault, correct. 1 is requested, page fault, correct. Now 2 is requested. So which of the following have been least recently used of 7, 0 and 2? That is 7, right? So 7 will be replaced. 0 is already present. Now 3 is requested. Now which have been least recently used between 2, 0 and 1? We just look at this history. We see 0 has been used recently. We see 2 has been used recently. But 1 has not been used for a long time. So we will replace 1. Right? So that is how your replacement occurs here. 0 is already present. Now 4. Again we will look at the history. Which has been used recently? 0 and 3 has been used recently, but 2 has not been used for a long time. So 2 will be evicted. Page fault. Next 2. So we'll look at the history, which has been used recently, least used recently, that is 3. So we'll evict 3 and 2. Then the request is 3. Again same, which has been used recently, that is 0. So we'll evict 0. Now 0 is requested. Again we will use the same technique. Which one has been least recently? 4. So 4 will be evicted. Now 3 is requested. 3 is already present. 2 is requested, already present. Then 1 is requested. So we will look at the window and check which has been the least recently used, and that is 0. So 0 will be evicted. 2 is already present. Then when 0 is requested, there it is not already present. So we will again look at the history to find out which has been least recently used of this. So 3 has been the least recently used. So 3 is evicted. 1, 0, 2. 1 is requested, already present. Now 7 is requested. So which of the following has been least recently used? 2. 2 is evicted. Fine. Then 0 is requested. 1 is requested, already present. So we find out 1, 2, 3, 4, 5, 9 and 12. So there are 12 page faults. So So LRU has less false than FIFO, but it is greater than optimal, right? So so it is better than FIFO. Now we can guarantee that. So this is a better algorithm than FIFO, but not as good as optimal. But okay, optimal. Who knows the future? So it is very impractical solution. So how do you implement it? So you keep a counter of each page table has a under counter associated with it. Every time a page is referenced to this entry, the content of the clock is copied into the counter. So basically, like if you have a programming queue, you know how to implement it. So if in the page table you get a reference that which one of them has been at least recently used and all, or you can keep a stack kind of thing to do it. So so this is LRU. So one thing is sure that LRU requires a special hardware. It is little slow than FIFO. Special hardware you know because you need to need to reference the history. So the hardware should be counters like nothing more. So any doubt regarding LRU? Okay, so let's go to the next one. So this is a stack to record the reference, the most recently used pages reference. So these are basically the hardware examples, like how you implement the LRU in your hardware. So you can do a stack to do it. So to get efficient implementation, we use an approximation. So LRU approximation algorithm. So to get an efficient way, we use an approximation of LRU. We use an approximation of LRU. So reference bit, each page associates with a hardware provided bit, initially 0. So when a page is referenced, the associated bit is set to 1. Replace any page with reference bit 0 if any exists. Okay. So basically it is something like this. Let me see there are examples. Yeah, we'll do it. So let's look at and do it first. Then we will go. Second chance one is that if FIFO scheme, so page to be replaced has reference bit 0, replace it. If reference bit 1, then set the reference bit to 0, leave the page in memory, replace next page subject to the same rules. Okay, let me do. Let's look at this. So so you have a set of let's say set of let's look at this one only. 1 2 3 4 1 1 2 5 1 2 3 4 5 1 2 3 4 1 2 5 1 2 3, 4, 5. So let's say there are 3 frames. Okay, and each page has a reference bit. So what you do is, in this second chance algorithm, what you do is initially let's say you load this one and you set the reference bit. Let me represent the reference bit as r. Okay, uh, let me set the reference bit as something like this. Let me use a different bit. So initially the reference value will be 0. Okay, then you enter here 2 and 3, and all of them's reference value will be 0, 0. Now your request, new request comes in as 4. You replace this one. Okay, and because its reference is currently 0, so you can do it. So you just check from top to down which one has a reference 0. So you replace it with 4. Then comes 1, not present, replace it with 1. Then comes 2, not present, replace it with 2. Now let's come 1. So what you do here, the reference count you make 1. Okay, so next comes 2. 2 is also present, you check the reference count as 2. Now comes 3. Now which one you will evict? The solution is the one which has 0. So you will evict this one. So you will put 3 here. Now next comes 4. So, and you make it 1. At the same time, what you will do is, you will make the rest 0 when this happens. So at next 4 comes, so it will evict 1. Then, and make it 0. And then 5 comes, it will evict this one and it's 5. So that is how this cycle happens. Okay, so this is another way of this your least recently used algorithm. So if reference bit is 0, replace it. If reference bit is 1, then set the 0 and leave the page in the memory. Replace the next page. So if you look at this, here is the reference bit. So this is the next victim, just replace it. So you can again enhance this one. So improve the algorithm by using a reference bit and a modify bit if available. So you can like this can be even extended further. That what this means. So 0, 0 not recently used, base page to replace. Not reduced, not modified, not recently used but modified, those things. So use a clock scheme, these kind of things. So these are some enhanced version of your least recently used algorithm. And this circular clock is basically used by your Unix. So this circular LRU is basically one that has been used by Unix. Let me see if I have an example or not. Let me see if I can draw it up. Yeah, you can ask. Yeah, you can ask. Fork is equals to 0. Yeah, this is very basic, right? How many times it will be printed? OS will be printed. Uh, Let me think. Yeah, okay, let me check. Let me do it. Uh, so you have if fork equals to 0. Just let me correct it, okay? If fork into this. Have I copied correctly? Have I copied correctly? Yeah. So yeah, answer will be 2. It is correct answer. So you see, uh, I have discussed this previously. So initially there is one parent, right? There is one parent. So what happens here? The parent remains parent, and a child is created, right? Let us call it C1. So there will be two copies of this. So uh, when will this part of the copy will be so when will this part of the one will be executed? For the child, this one will be executed, right? So this one will be executed only for the child. I mean, it will be printed one. Are you sure that this one was the answer? Because I think it will be printed one because C1 will execute this part. This part will only be executed by C1 because the child will only get it. So so this fork will create two things. So C1 and its child C2. So and this part will be executed by not the child of C2, not C2, only by C1. Only this will be able to execute it. That means it should be one time only printed. So if you run the code, it will be one time only printed, right?
That's audible.
Haha.
So this is basically question week 3, question number 30.
Question number
So I had question number 30,
from where?
week 3.
Week 3. So it has been released. Let
Yes,
me
the solutions are also released, and in solution they have given correct answer as C, that is.
let me check. Okay, 1 minute. Yeah, I got it. Let me check the solution once. What they have done. Question number
13, 13.
13. Have you run the code?
Yes, I have also run in like online compilers. So there I am also getting answer.
You are getting one only, right?
Yes.
That's what I am also thinking. It should be one only. I mean, it
We
should
need
be.
to ask in that ask a question section. There is a discussion section.
Yeah, Yeah, so in the
I
forum
think
you can ask, but I think it will be one only because if you run the code, it will be one only printed.
yes, because for parent the fork will return the
Yeah,
PID
fork will
of the
return only
child.
for the parent
So
only.
the outer for loop
No, no,
will
yeah.
not run for parent, right?
So yeah, so it will be only for
And
C1 for one child.
uh, and for child also, uh, for C1 it will only print operating system. For C2 child it will return 0 to the child. So so the inner for loop if will not get
Yeah,
executed.
so it will
So
be
it will
C1. What I
and
have written here is this one only will be executed. So only C1 will execute it, not C2 or P. So
so I had this doubt I thought
yeah,
this
you can ask in the forum
if you
that.
ask in discussion.
Yeah, you can ask in the
Yes, yes,
discussion forum that.
in discussion.
So what you can do is you can run the code and you can paste the solution also there. So
Yes, yes.
yeah, so you can give that as a screenshot also that this is the output I am getting. They should revise it. Because I don't know who gives the assignment and all because I am not involved in that. So they should modify it.
Yeah, the one who is the problem setter for this assignment, that same personality is solving the doubts of the students in the discussion forum. So you can ask him.
So you can just paste a screenshot that okay I am running the code and I am getting only one. So that should be okay. Yeah. Okay. So let's come back to this. So what I was showing you is something like this. This is your uh, this is your example of this clock one. So first two comes, then three comes. So you will so you notice this part. This is a counter just to maintain your so that 0 1 1 concept here. So you remove the one which has not been previously used and reset all of them as 0. So see when 5 comes there is a fault, and at the same time you update 5 and remove the bits of others to 1 from 0 to 1, 1 to 0 or something. That's what I meant to say. So this is your clock example. Okay. So let's counting algorithms. So counters and all replace pages with the least count, least frequently used, most frequently used. That are also there. So instead of the just not only the memory, only memory, but also count the memory. And most frequently used based on the argument that the page with the smallest count was probably just brought in and all. Then there is some page buffering algorithm. So keep a pool of free frames. When a page fault occurs, a victim page is chosen as before. The desired page that needs to be brought into the memory is read into one of the free frames from the pool before the victim page is written out. Start the process immediately. Maintain a list of modified pages. Possibly keep a pool of free frames and all. So this is nothing important much. Not much important. So allocation of frames and all. some frame allocation examples. So size of the process, total number of frames, allocation for PI and all. So the equal allocation split n frames among n processes equally. I mean, these are nothing extraordinary to remember, and not much important also. And then there comes this. So global replacement versus local allocation. So in global replacement, process selects a replacement frame from the set of all frames. One process can take a frame from another one. Local replacement, each process selects only from its own set of allocated frames. So in global allocation, so you need a free frame, you select anyone which is free. It doesn't matter which process is currently using it or not. But in a local replacement, what happens? Each one, each of your frames have been allocated to a certain process. Okay, so this is controlled by P0. So when P0 needs, so when P0 gets a page fault, uh, you need to consider only these frames, right? So it cannot, it has, for replacement you need to consider only the frames which has been allocated to it. Yeah, it will be available on the YouTube channel. Okay, so next we come to the concept of thrashing. So what happens what happens in your paging process? So suppose you have pages like this which are currently all occupied. So these are all of them are occupied, and let's say you evict this one. So you evict this one, you evict this one out, and you brought a let you brought a new one in. You brought a new frame in, a new page in. Now, let's say in the next iteration, you again need this one only. So there will be a case of continuous page faults where pages will be continuously swapped in slash out, right? So the pages will be continuously swapped in and out irrespective, in a continuous process. So that is what is called thrashing. So page fault, so the rate of page fault is high, so page fault rate is high, replace existing frames and all this. What happens, the problem with thrashing is that it leads to low CPU utilization. Operator system thinks that it needs to increase the degree of multi-programming. Another process is added to the system. Thrashing, a process is busy swapping pages in and out, so that is basically your thrashing. So this is a medium of this thrashing. So initially the multiple program CPU utilization is low, and after this point thrashing occurs. So 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 what is the difference between demand paging and thrashing? So thrashing occurs when the size of the locality, total size is greater than the total memory size, right? So demand paging work is a locality model. So process migrates from one locality to another locality. Localities may overlap, but if the total size of the locality is greater than the total memory size, then thrashing occurs. So thrashing can be limited by using local page replacement, priority page replacement. These are the two concepts. So demand paging is basically is getting the page in only when required, but the size is small, then thrashing occurs. So that is what it says. These are some memory location locality related concepts, working state model and all. Not much important. Keep it track of. So this is again the graph which you are saying, that page for number of page faults and the relation between the number of page faults. So as you can see, so at the same time, at the as the number of frames increases, the page fault decreases at simultaneously. Okay, so with that we end this week's revision. So let's now solve some problems. So let's come back to this. So let's start with question number 1. So for a page reference string, so these are the strings you are given. So we need to compute the number of page faults that occurs in this case. So initially it is empty. So initially, so there are 3 frames. Let's look at this. So initially 2 is 1, so 2 is not present, so it will be a page fault. Then 3 is brought in, another page fault. Then 0 is brought in, another page fault. So we are using the concept of LRU. So then 1 comes. Which one are the least recently used? That is 2. So 2 will be replaced, another page fault. 1, 2, 3, 0. Then 5 comes. Which one was the least recently used? 3. So 3 will be replaced. 1, 5, 0. Now 4. Which one was the least recently used? 0. So 0 will be evicted. So it will be 1, 5, 4. Now 0 comes. Which one was the least recently used? 1. So that will be evicted. 0, 5, 4. Okay. So then 1 is requested. Which one is the least recently used? 5. So that will be replaced. 1, 0, 1, 4. So which one is the least recently used now? 4. So now 2 comes, 4 is replaced. 0, 1, 2. Okay. So then similarly 5 is comes. Which one is the least recently used? 0, 0, 0 is replaced, sorry. 5 is replaced, 5 1 2. Then there is 4, 1 is the least recently used, 5 4 2. Then 3 comes, which one is the least recently used? 2, 5 4 3. Then 4 comes, 4 is already present, no page fault. Then 2 comes, not least recently used, 5 2 4 3. 3 comes, 3 is already present. Then 5 comes, which was the least recently used, 4 2 5 3. So there are number of page faults: 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Correct. So the correct answer is number B, 14. 14 is the correct answer. Okay. So let's go to the next one. So optimal page replacement algorithm always has the lowest page fault among all the algorithms. Will never suffer from Belady's anomaly. Difficult to implement as it needs future knowledge of the reference string. We have studied the optimal page replacement algorithm, and we saw that it has the lowest page fault among all the algorithms. That is true. Optimal is less than LRU is less than FIFO. Will never suffer from Belady's anomaly. Yes, only FIFO suffers from Belady's anomaly. This is also true. Difficult to implement as this needs future knowledge of the reference string. True. We saw that it has to know what happens in future to predict the present. So to decide in the present. So this one is also true. So the correct answer is all of the above. Okay, so let's go to the next one. Select the incorrect statement regarding thrashing. Local page replacement can limit the effects of thrashing. Incorrect statement we have to predict. So local page replacement algorithm can limit the effect of thrashing. So this one is a true statement, is not incorrect. We saw that local page replacement algorithm can limit the effect of thrashing. Even a priority page replacement also can limit the effects of thrashing. Thrashing occurs when the size of all locality exceeds the memory size. True, thrashing occurs when the size of all locality exceeds the memory size. So all of them are correct. So the correct answer is none of the above. So I think this is clear. Okay, so let's go to the next one. Which of the following page replacement algorithm exhibits Belady's anomaly? So what was Belady's anomaly? That while uh, so so logically, if we increase number of frames, page fault rate should decrease, but in Belady's opposite happens, right? So uh, we have seen the one that page replacement algorithm that exhibits it was uh, FIFO. We saw that previously that for so we have seen in this experiment here, like here, so that if we are using 3 frames, we got 9 page faults, but when we are using 4 frames, we got 10 page faults. So this is your B lady's anomaly, right? So let's come to question number 5. When a page is selected for replacement and its modify bit is set, when a page is selected for replacement and its modified bit is set, the page is clean, the page has been modified since it was read from the disk, the page is dirty, and the page has been modified since it was read from the disk, and the page is dirty. So the correct answer is D, because it indicates that the page has been modified since it has been read from the disk and the page is dirty. So what happens there? Copy on write happens. Not copy on write, it has to be let's say not only swapped out but also written in memory, right? This is what happens. Okay, so let's come to the next one. So you have to a correct order of basic page replacement you have to select. So page number 1 is page replacement is used in the case there is no free frame. Page replacement algorithm is used when there is no free frame. Then the process is continued by restarting the instruction caused by trap. Location of the desired frame is found on the disk. Desired page is washed into the new replacement field and all. So first 3 happens, right? So first the location of the desired frame is found on the disk. Then what happens? Uh, page replacement algorithm is used in case there is no free frame. Then what happens? Desired page is brought onto the newly freed frame, and page and frame tables are updated, and then the process is continued by restarting the instruction caused by a trap. Right, this is the order, and the correct answer is option C. Okay, so let's go for the next one. So you have this. We have to match the following. So reference bit 0, modify bit 0. So that means that is the best What does this mean? That is the best page to replace, right? Which we have done. Reference bit 0, modified bit equals to 1. Must write out before replacement, right? So that will be P. Reference bit 1, modified bit 0. Uh, Reference bit 1, modified bit 0. So that will be S, probably will be used again. It has not yet been modified. Reference bit 1, modified bit 0. Probably also will be used again, but need to write out before replacement as well. So it will have to be written out. So reference bit indicates the history, and modified bit represent uh, state of the data. Now let's come to question number 8. The aim of creating page replacement algorithm is to replace page faster, maximize the page fault rate, minimize the page fault rate to allocate multiple pages to the process. So the correct option is option C. The our optimization is basically minimize the page fault rate. Okay, so let's come to the next one. A page replacement algorithm replacement occurs when free frame becomes available, a page fault occurs, and we need to bring the desired page into the memory. Multiple pages are allocated to the process. So option is B. A page fault occurs and we need to bring the desired page into the memory. Right. So that is question number 9. Question number 10. Which of the following replacement is correct about statement is correct about the replacement policy? Local replacement policy consider all block pages in the main memory as candidate for the replacement regardless of which process owns a particular page. Global replacement policy shows more consistency per process. In local replacement policy, process selects a replacement from all sets of frames. So this is false. A global replacement policy has greater throughput and thus is most commonly used. This is true. It has more throughput. This is false because it is local replacement. And this is also false. This is the correct answer. So thank you for joining. That's the end of today's session. We will meet again next week, same time. Thank you.